Today we'll start talking about the theoretical basis of cosmology, general relativistic cosmology, which is of course established by Einstein 100 plus years ago. And just to refresh your memory, in 1905 he published a seminal paper establishing special relativity, which was a very fundamental change in viewing space and time and electromagnetic interactions. And it starts with postulate the equivalence of all unaccelerated frames of reference, which solves a long-standing but neglected problem of interpreting classic electrodynamics and explains the failure of Michelson-Morley experiment and precession of Mercury's orbit and so on, and makes some interesting predictions. First of all, the speed of light is the maximum velocity to which some material body can be accelerated, and not beyond that, will require infinite energy. And it's a little misleading to say it's the speed of light. What's so special about light? No, it's really some sense special. It's the speed of space-time. It's just that light or any other massless particles move with the largest speed they can. So we now know that also gravity propagates at the speed of light and makes predictions of things like Lorentz contraction and time dilation and so on. So that is a special relativity because it has to do with just unaccelerated frames of reference. And then Einstein expanded it to include all frames of reference, which became the basis for general relativity some 10 years later. And you've probably seen the thought experiment with rockets and springs and so on, how gravity is really fictitious force, because you couldn't tell whether you accelerated downward gravity or by an accelerating frame of reference. And it is therefore a theory of gravity. So the general relativity in a nutshell is in this box that the presence of mass and energy, which are equivalent, determines what the geometry of the space is. And the geometry of space tells where matter and energy can go. And they usually go to the shortest distance between 2 points, which is different in curved spaces. So that was an even more fundamental change in our thinking about space and time and gravity, of course. And he made the predictions of things like light deflection by masses as it's passing near potential well, gravitational redshift, now gravitational waves, which are another prediction, which was spectacularly confirmed a few years ago. And it's based on so-called equivalence principle. Einstein started with so-called Mach's principle, which is a philosophical principle, not physical. And Mach's hypothesis was that gravitational interaction or inertia is due to all of the mass in the universe, which is not exactly the same thing as his equivalence purpose that says that any accelerated frame of reference is indistinguishable from any other with same acceleration. And so there are also, if you can think about it, two different ways in which mass entered Newton's physics. One was as a measure of inertia, and the other one was as a source of gravity, if you will. And there was no a priori good reason why should those two things be the same. Well, Einstein says naturally, yes, they're the same because of the equivalence principle. And that was confirmed with Etwer's experiments and many that followed. So that these two predictions resulted from solving Einstein's equations. The light can be blue shifted or red shifted, depending whether it was into the potential well or out. And the paths of light rays will be curved according to the geometry of space-time. So he realized that very quickly, in fact, at the very beginning of his studies, and he reached out to George Ellery Hale, who was then probably the most famous observational astronomer in America, and asked, could we possibly observe light deflection around the sun? And Hale basically said no. because it would be a couple arc seconds and will require you to obscure the sun, which of course could happen during a total solar eclipse, which was realized by Eddington, who organized the famous expeditions to observe solar eclipse in 1919. And that confirmed general relativity with a very good degree of accuracy, which has since been confirmed better and better and better. And that's when Einstein really became famous, because it was completely changed the way people looked at space and time and gravity and so on. And he became like the the best known scientist in the world, and maybe even still is. Okay, so, how does this go about? Remember, so the basic idea is you have presence of mass and energy that changes the local geometry, and local geometry tells mass and energy where to go. And if you can solve that in a self-consistent fashion, then you got general theory of relativity. So that is basically accomplished by Einstein equations, which are a tensor equation. And we will not go through this, so just going to show you what they look like. So in a complete form, they're written like this. G on the left side is a 4x4 tensor, space-time, 4 coordinates, that describes the geometry. And on the right-hand side is this T, nu, which is also 4x4 tensor that describes the distribution of mass and energy. And so there are all these other quantities. You don't need to know that. But remember, this is 16 equations for each pairwise combination of components of space and time. Now, we introduced certain symmetry principles, namely that the universe is homogeneous, same everywhere at a given time, and isotropic, same in all directions. That automatically removes all off-diagonal elements of the tensor equation. The off-diagonal elements have to do with tension and stress, and in the universe at large, they're not important. They're important in places like near black holes and so on. So people who do numerical simulations of black holes and so on have to worry about all 16. And then, if the universe is isotropic and every direction is as good as any other one, the 3 spatial coordinates can be reduced to 1, the radial separation. So from 16 equations, you get 1. And that's what's known as the Friedmann equation, which is what we use to describe dynamics of the universe. Just a few other items about how was that set up. Well, you describe geometry through metric, which is what's the separation of 2 points. And you're all familiar with Pythagorean quadratic sum, delta dx squared plus dy squared plus dc squared gives you the square of linear separation. But there is also now time, right? So these indices are traditionally written from 0 to 3 instead of 1 through 4. 0 is the time component, the 3 are the spatial xyz components. And the separation is a quadratic sum of mutual combinations connected with these coefficients called metric tensor indices. And each of them can be a function of things, position, time, wherever. So in the simplest Euclidean case, all terms that are not the same of diagonal terms are 0. And just diagonal terms are 1, 1, 1, right? For time, it is actually taken to be -1. So the special case, the Euclidean space that includes the time, is Minkowski's space-time metric, which you may have encountered in special relativity, and it's written like this. Now, for general relativity, there is a more complicated formula called Robertson-Walker metric, which actually originated at Caltech. And it's written here, and you don't need to remember much more about it. Here it's written in general polar coordinates, but if only radial coordinate is important, only the radial direction matters. And there is a little constant, k, which is so-called curvature constant, tells us whether space is negatively curved, flat Euclidean, or positively curved. I'm showing this for completeness sake. We will not probably be using this because we will always assume homogeneity and isotropy in deriving the Friedmann equations. Okay, so remember Einstein encountered an integration constant in his equations, which we call cosmological constant, and he used it to balance attractive force of gravity to keep universe stationary, which later he called his biggest mistake ever because he failed to predict the expansion of the universe. So just coming up with cosmological constant was not a mistake. Essentially, he uncovered that there is another constant of nature on par with, say, Newton's gravitational constant, which still plays the role. But back then, there was no physics to explain it. Still, there is no physics to explain it. And so people kind of tend to ignore it and assume it's zero. I mean, that is what usually a good advice is when you're solving a physics problem. If you don't know what the result is, just say it's zero, because then you don't have to worry about units, right? Okay, so remember that. That came as a natural constant in general relativity, and nobody knew what its value was, or even what sign it had. So I mentioned isotropy and homogeneity, and that is what helps us go from 16 equations, 16 partial differential equations, that's one tensor equation, into the single ordinary differential equation. And it's called cosmological principle. In some sense, it's an extension of the Copernican principle. It says that universe at given time is same on average in density in all directions, in all locations. And of course, there are local irregularities that can cause local velocities and so on. But on really large scales, that's what is assumed to be. You may also remember there was a steady state cosmology which added one extra thing saying, okay, not only is universe same in all places, in all directions at a given time, but it's also same at all times. And since it was known that the universe was expanding by then, that required to come up with new matter to fill up the gaps in some sense. So that was the so-called steady state model. The universe is expanding, but there is always same picture on large scales, which was then disproven by observations of things like radio sources and most of all cosmic microwave background. But here it is just for completeness. So what do we mean by homogeneity and isotropy? All right, here's just a cartoon version. The square on the upper left is homogeneous, kind of same everywhere, but not isotropic. There is preferred direction. And the circle on the top right is isotropic at central point, but it's not homogeneous, right? Whereas homogeneous and isotropic is just kind of uniform mush. And that's the idea, that everywhere you are in the universe, in all directions, things are going to look the same on average. Well, is this true? These are huge assumptions. And at the face value of it, well, no, look, there are galaxies and clusters and whatnot. But on sufficiently large scales, it's an excellent description of the universe. So what's shown here, in the upper right, is positions in the sky of radio sources from a particular radio sky survey. And each dot is some radio source, and they're all kind of gigaparsecs away, many gigaparsecs away. And it looks pretty darn random, yeah? So that's true. Once you go past some tens of megaparsecs, 100 megaparsecs, the universe is pretty uniform. The best evidence we had for uniformity is for microwave background. This is my cartoon picture of what cosmic microwave background sky looks like. It's very uniform. How uniform? 2 parts in a million. Now, those parts in a million are actually very interesting, but to an excellent approximation, universe on cosmological scales really is homogeneous and isotropic. I mean, not quite isotropic because our galaxy has particular velocity relative to the microwave background photons, but that's all right. So here is a slice through one of the more modern redshift surveys, that's so-called 2DF Galaxy Redshift Survey, and it is centered on us, and the two cones are like directions in which they map the sky. Each dot is a galaxy, and you can see that, well, galaxies are not uniformly randomly distributed. They're all these structures, a large-scale structure of the universe, of filaments and voids and clusters and so on. But the scales of those are up to some tens of megaparsecs. And as you go to a larger scale, it all kind of averages out. They're fading outwards because of the flux limits of the survey. You just don't measure galaxies that are further out. So that's okay. So locally, the universe is not necessarily homogeneous and isotropic, and it isn't, and condensations of mass will then perturb universal expansion. Masses will create acceleration, acceleration will create velocity, and we'll talk about that later in the class. So by and large, if you're looking just the universe as a whole, large scale, yeah, it's homogeneous and isotropic to a very good degree. And so now some obvious questions arise, like it's expanding, but what do you mean expanding relative to what? And right away, that tells you have to have two different kinds of coordinates. You have to have the coordinates that do not expand and coordinates that do expand relative to those that do not. Those that do expand, kind of this intrinsic coordinate grid of space-time, it's called co-moving coordinates. Co-moving because things that are fixed in those coordinates are kind of moving along as space moves apart. And what belongs to those? Well, any of the unbound systems, like say galaxies that are not bound by gravity, or planets or stars, they do not expand with the expanding space. They're held together by whatever is the interaction that's holding them together. And also wavelengths of any massless particles, photons, gravitons, others if they exist, also stretch as the space stretches. And then there are proper coordinates, which are those that you know and love, that are coordinates you read off on your ruler, which is held together by interatomic forces. So the sizes of atoms and molecules and galaxies and so on, they do not partake in the universal expansion. Okay, so there are two coordinates, and we'll have to pay attention to that as we go forward. And then the question is, what is it expanding into, right? Well, there is no edge of the universe, and it's kind of expanding into itself, which sounds like a tricky answer, but look at two possible arrangements. One is, think of it as a two-dimensional sphere embedded in a 3D space. So the two-dimensional sphere can be expanding, but if your world consists of the surface of that sphere, you know, it's not expanding into its own surface. It's expanding in this third coordinate, which you can think of as time. Time would be the radius, if you will. Alternatively, it's not positively curved like a sphere. It could be flat Euclidean or hyperbolic, and you lay down coordinate grid like a graph paper, and it can be stretching out in all directions. It can be infinite and stretching relative to a fixed piece of graph paper that doesn't stretch. And so there is no edge, and there is no center. On the spheres, we lay down coordinates to make two special points, the poles. But in principle, you can twist the coordinate grid anywhere you want, so every point is still as good as any other, right? The sphere just expands. So the space does expand uniformly everywhere. There is no preferred center, so you can tell your friends that, yes, actually, I am the center of the universe, and so is every one of them. But it's a good thing when you it's late at night, right? All right, so then that sets the stage. And What will describe then models of space-time, kinematics of space-time? We'll introduce this quantity called scale factor, which is distance between any two co-moving points, two galaxies far apart or something like that. And any two will do fine because every point is as good as every other, right? So sometimes it's called R, capital R of t, sometimes lowercase a of t. I'll try to stick with lowercase a because that's what Schneider's book uses. And if you just pick these two spots in the co-moving coordinate grid and find how is that separation changing in proper coordinates, those that did not expand, as a function of time, you got everything you need because any 2 points will do the same thing. So how do we figure this one out? Is by solving so-called Friedman equation or Friedman-Lemaitre's equation, which is the one differential equation that's remaining from Einstein's 16 with the assumptions of homogeneity and isotropy, radial separation in time of any two co-moving points. Okay, so how does this work? If you start with some co-moving distance x, right, and sometime later, the radial separation of those 2 points will be original separation times that expansion factor, a of t, right? So usually convention is that for here and now, we use subscript 0. And then at other times, it's something else. So if you ask what's the velocity of separation of 2 points, well, it's an obvious equation here. If they can take the expansion factor out of it, and so essentially it is the time derivative of the expansion factor times the original separation. And it looks like velocity is some constant or parameter times the radial separation. And the constant is normalized expansion rate, a dot over a. So it has dimensions of 1 over time. All right? Well, that's nothing but the Hubble's law, that expansion velocity, apparent expansion velocity, is proportional to the separation of the points. Another way to think of it is, well, at some point, things move by a little delta r, and some further point will do some different delta r, and since the whole thing is scaling in the same way, the displacement will be proportional to the distance because the delta t is the same, right? Okay? So that explains the Hubble's law. This is how Hubble's law was immediately understood, that it represents the uniform expansion of space in co-moving coordinates. A note, however, that over today, now, here, we note this value of this proportionality constant, Hubble constant, as h subscript naught, h naught, and it really isn't. If you wait another billion years, it's going to be something else. So it's really a parameter and not a constant. But over the short periods of time, like human civilization, it's pretty darn close to be constant. So that's why we call it Hubble constant, because locally it is, and it will change, and it was different in the past, but now it's what it is. And it's roughly speaking 70 kilometers per second of velocity for each megaparsec of distance, give or take a few percent. All right, well, the expansion, yes?
How do we know that it's changing the constant?
How do we know it's changing? It's because that will be a natural consequence of the models that we're about to go to, right? Short version is, well, universe is expanding. It has some self-gravity, which will tend to decelerate the expansion. And so Hubble's constant or parameter was almost guaranteed to be higher in the past. The universe slows down its expansion until there is something that starts accelerating it, but there is, that's the dark energy. So that will be part of the cosmological models. All right, well, we measure velocities through Doppler shift, how much would lines of different elements change as we observe different galaxies, and think of it as the Doppler shift, and it is, except it's not quite. So for non-relativistic speeds, it's the customary formula of velocity divided the speed of light gives you the red shift. For special relativity, it's a little more complicated given by the formula that's up there, but that's well understood. However, usually we think of velocity as something that's product of some acceleration by some force. In this case, galaxies were not accelerated by any force. They were just taking a ride on the co-moving coordinate grid. So it's not quite the same thing. Nevertheless, for consistency's sake, it turns out to be the exact same thing as you would say, oh, this is Doppler shift. And the usual analogy is this expanding balloon that you can think of now as our 3D universe as a two-dimensional surface of a balloon. You glue little dots on it, there are galaxies, and you draw some wiggly lines, which are the photons flying between them. As you expand the balloon, the photons will stretch, but the galaxies won't, right? And so essentially the change in the wavelength of the photon is direct measurement of how much has the universe expanded since that photon was emitted, right? So the ratio of the observed wavelength to the emitted wavelength is the ratio of the expansion factors, now and then. And that's 1 plus redshift. So 1 over 1 plus redshift is the expansion factor that happens. So if we measure redshift to some galaxy to be, say, 1, that means the universe doubled in size since then. If the redshift is 10, well, then the universe expanded by a factor of 11 since then. And cosmological models are letting us figure out how much that really is. All right. So, yes?
Is the reason that galaxies stay the same size is because their size compared to the universe is really negligible?
No. The galaxies or stars or planets, the solar systems stay the same because they're bound systems and they do not partake in the expansion of space. Things that are bound, have negative total energy, do not partake in the expansion of space. Right? All right, so real Friedmann equation or Friedmann-Lemaitre equation, depending, because they're kind of independently derived by two of them, requires going to general relativity, but you can do a pretty good job just by doing a quasi-Newtonian derivation. Why? Because we're talking about very low gravitational fields, very small speeds locally, and so Newtonian approximation is going to be pretty good. All right, so you take any point in its space, and they're all just as good as any other because of homogeneity and isotropy. Put a sphere of some radius, r, pick a point on that sphere. All right. Now, you probably remember from Newtonian gravity that when you have a situation like that, gravitational acceleration is only due to the stuff that's interior to that radius because stuff outside cancels out. So that's called Birkhoff's theorem. All right. So let's look at the acceleration of this test particle on the surface of the sphere. And the enclosed mass for uniform density, again, homogeneity, will be volume of the sphere times the cube of the radius, which you can write down in co-moving or proper coordinates using the expansion factor. All right. So if mass is conserved, the expansion would dilute the density by the cube of the expansion factor. That's kind of obvious. Incidentally, it will not be the case for the radiation, because radiation will dilute the number density of photons by the same factor as the volume. But each photon would also get stretched by 1 extra power of expansion factor, so it'd be like 4th power, not 3rd. And for dark energy, it would be even weirder. it will stay the constant. Right. Okay, so here we go. So you can write down the differential equation of the change in radius, acceleration, and all of you can do this. Transform into the proper coordinates, or rather common coordinates. And I suggest that all of you kind of walk through this derivation, which is also given in Schneider's book, just to kind of gel it in your own minds. And you can then change this by multiplying again by 2 times a dot, integrate in time. There are these 2 substitutions you need to make. And you can do this on half a page if you do it yourself. And you get an equation that looks like this. And since you've been integrating the second derivative into the first derivative, you have integration constant, right? And that is written as k times c squared. And k is so-called curvature constant. Since the units of expansion factor are arbitrary, we can always choose the value of this curvature constant to be 0, +1 for closed universe, positively curved, -1 for open universe, negatively curved. All right. So that basically is quasi-Newtonian Friedmann equation. And if you look at it, it kind of reminds you of the conservation of energy, where the kinetic minus potential to absolute sign is equal total something, right? So actually, you can then move this to the other side. And so the sign of the curvature will determine, are you talking about something is bound or not? So if this constant k is equal to 0, it corresponds to flat Euclidean universe that you know and love, which amazingly enough is pretty close to what the real universe is like. Well, then a dot squared is equal to this finite quantity on the right side of the equation, and so universe will expand forever. But as scale factor goes to infinity, the velocity will go to 0. So it's just like a parabolic orbit for Newtonian gravitationally bound system. Now, if k is negative, the negatively curved open universe, then yes, a dot squared is going to be positive at all times, and in the infinite future, as a goes to infinity, the speed goes to the speed of light. Basically. So this is like a hyperbolic orbit for Newtonian case, right? Now, if k is positive, positively curved closed universe, well, that would correspond to a negative total energy system that was bound. What will happen then is, at some point, because the sign of kc squared is positive, subtracted from the other one, there is going to be a time when the derivative is equal to 0. The velocity, expansion velocity goes to 0. And that happens at this particular value of the maximum expansion factor. And because the second derivative is always less than 0, because gravity is only attractive and it's slowing down the expansion, at that point, expansion turns around and the universe recollapses upon itself into essentially an opposite of Big Bang, also known as the Big Crunch. And so for the longest period of time, we didn't know what's going to happen. Now we do. The universe is going to expand forever. So geometry, which is given really by the density, really determines the fate of the universe if we ignore cosmological constant for the moment. And so the global geometry of the universe, then showing these two-dimensional analogs of three-dimensional space-time, you can have positive curvature, like surface of a sphere. The sum of angles in a triangle is greater than 180 degrees. You can have negative curvature, like a saddle. The sum of the angles in a triangle is less than 180 degrees. And good old fashionable Euclidean space, where sum of the angles in a triangle is 180 degrees. And that seems to be more or less the universe we live in. And there seems to be good reason for that. Okay, so that was sort of Newtonian intuitive way how to get to this point. And if you do proper math, going from tensor equations and so on, you come up with, well, pretty much the same equation, right? Except that now it's got also this mysterious lambda term, cosmological constant term added to them, which makes life a lot more interesting, as you will see next time. And you also account for pressure of the material. These two equations are really not independent. One can be kind of derived from the other, but both are given as Friedmann-Lemaitre equations. And so, again, they're essentially equation of motion for the whole universe. As it expands and then maybe contracts or maybe accelerates, it depends on densities and pressures that are involved. Here, rho is the sum of all matter energy densities that are present, which, as far as we know, consist of regular matter, including dark matter, particles of some sort, radiation, photons, maybe some relativistic neutrinos, and vacuum energy density, which is what cosmological constant really is all about, which was the big surprise once that was shown to be actually real. And we will talk a lot more about that later on. At the same time, pressure is sum of three pressures, gas, but gaseous pressure is proportional to the speed of sound, and as long as that's much, much less than the speed of light, yes, go ahead.
So you said the rho term includes both lambda, like dark energy, even though there is a lambda term?
Oh, I'm sorry. Yeah, I confused this. Not in the top equations, but thinking ahead, yes, we will be considering all three components. Yes. Good catch. So pressure of the ordinary matter, it tends to be much, much smaller than relativistic gas pressure. And so it's basically zero. So we call ordinary matter galaxies dust. There is pressureless cosmic fluid. It's just contributing mass energy, mass density, but not pressure. Radiation, however, always does have pressure. And radiative pressure is given here, and energy density of radiation is equivalent to some equivalent mass density times c squared. Rather, it goes the opposite. You have radiation energy density, usually called little u, and you divide it by speed of light squared. That will give you, if those photons, well, they create as much gravity as the mass of that density would have. And then there is this vacuum density that corresponds to the dark energy, or cosmological constant, which is constant, as cosmological constant implied. So even the universe expands, each proper cubic centimeter still gets the same number of ergs or joules or whatever. And normally, in thermodynamics, if you expand the volume, the energy content of that volume is going to get diluted. But if it doesn't, if it stays constant, well, then you ought to have negative pressure because it's du is pdv. And so this strange new dark energy has strange properties. It's got negative pressure and positive energy density. And it doesn't change even the universe expands, which is very strange. All right, but all in all, the universe on large scales would follow these equations as it expands. And because now you have this extra lambda term, the simple hand-waving connection with curvature of space and positive or negative energy gets a little bit more complicated, right? For example, you can see that if you have positive cosmological constant and it acts as an accelerating force, that's the opposite of usual gravity, that's decelerating force, even though they're not forces, there is a point in which they're equal. And this is what Einstein first came up with, where cosmological constant value was chosen such to exactly balance the attraction of the self-gravity, which turned out to be an unstable situation. I'll show you this next time. Okay, so we will play more with these equations next time and actually derive some simple cosmological models. There's one more thing that we will need to introduce, which is what's called the equation of state. So this cosmological matter-energy fluid, if you will, fills the universe, if it's not fluid really, right? Its density, mass or energy density, depends on the expansion factor. And it depends on what it is. For the matter, dilutes as a cube of the expansion. For the radiation, as a fourth power of the expansion. For dark energy, not at all. And so they will have different behaviors, and that behavior is specified through so-called equation of state, which I'll introduce next time. And then different components will dominate the expansion at different times because their behavior with density is different. Okay? But before we go there, let's define some cosmological parameters. The first one we already defined, it's Hubble's constant, or parameter, if you will. And it has dimensions of 1 over time, because it's A dot over A. And here now, time equals t0. If we are sitting on some expansion curve, if you take the tangent and run it backward in time, it intercepts the time axis, and that is the Hubble time. 1 over Hubble time. Actually, I put my little wiggly bracket wrong. It should go to the intercept point. So the instantaneous normalized expansion rate would then define, in some sense, something that's close estimate of the age of the universe at that time. And if you multiply by speed of light, then you get size. And that c over h naught is called Hubble radius. And again, because Hubble constant is not constant, but it changes, Hubble radius changes. But it gives you kind of spatial estimate of what are the typical scales of the universe, which for the value we measure today is a little over 4 gigaparsecs. And indeed, the distance to the Big Bang, if you will, is several times that. Now, all these other, yes, go ahead.
Isn't Hubble's constant increasing over time?
I'm sorry.
Isn't Hubble's constant increasing over time?
No, it's, well, now it's in an acceleration stage, so it actually is increasing slightly. But for most of the past, it was decreasing because density of the matter was dominant, slowing down the expansion, and the last few giga years, it slowly started accelerating, so it's now increasing. Now, when we measure Hubble constant at any given distance to us, say microwave background, you know, we can use these formulas to map us. Like back then, it was so and so, and if you evolve it forward in time today, it will be this value. So we can compare what would be the different methods. Yes?
You said about the squiggly bracket problem. That was one question of where it's supposed to go to, and then also, can you explain again what Hubble time represents?
These curves have exaggerated curvature by and large. And so Hubble's law is linear law, right? And so if we were living in a purely flat space, then tangent on a straight expansion line will hit exactly at the beginning of the expansion. Because they're curved, it's not quite so, right? But nevertheless, the difference is not huge. It depends on cosmological parameters. You know, could be give or take 30, 50%, depending on cosmological parameters. But it gives you an order of magnitude of what is the age of the expanding universe at that time. Right? Okay. So that's one. The other parameters, which are really matter energy densities that govern, the attractive forces, are determining the shape of these curves. How much is deceleration happening? Is there acceleration? And so on. And they're parameterized through so-called density parameters. Oops. You can rewrite the cosmological constant Friedmann equation in this form, because remember, you can transform A dot into Hubble constant. And if you define this critical value of density today as 3 times Hubble constant squared times divided by 8 pi g, and then you divide the actual density by this critical density, which again is a function of time because Hubble constant is a function of time, you get what we call the matter density parameter. And those density parameters always denoted as capital omega. Subscript would indicate is the mass, radiation, whatever. And if omega is equal to 1, the universe is exactly the critical density, and it's Euclidean. If it's more than 1, it's positively curved, has to recollapse. If it's less than 1, it's negatively curved, it will open and expands forever. Which is why people who are saying cosmology density is the destiny. Yes?
What was that L parameter that is set to 0?
I'm sorry, it should have been lambda typo.
Okay.
Yeah. I'll fix that before I put PDFs online. Okay, well, vacuum energy density is another component, and it's related to the lambda constant by this equation, derived again by divided by the critical density, and it is now some omega sub lambda. So universe can have critical density just in this vacuum energy. But today we know that omega matter is about 0.3 and omega lambda is about 0.7. And so that's kind of total thing. Plus radiation, which I neglected here because today it's negligible, although it wasn't negligible in the early universe. In the old-fashioned days, they were using this thing called the deceleration parameter. So here I used R instead of A. Think of those big R's as little A's. And it's defined like so. And it's essentially a way to parameterize the slowdown of the expansion velocity. And you can see if there is no cosmological constant, it's exactly 1/2 of the density, critical density parameter. But if there is cosmological constant, then the two go against each other. And in fact, we live in a universe in which universe was first decelerated in the expansion. And then once the matter got diluted sufficiently, whereas cosmological constant didn't get diluted, it really started dominating expansion after a while. And so originally, the deceleration parameter, which had the minus sign there, was positive, decelerating, and now it's negative because the universe is accelerating. We'll say a few more things about that as we go into more detail later. I'm just defining the parameters now. Okay? So some real numbers, right? Hubble constant is usually parameterized as this little h, which is actual value, which has units. The units are 1/time, or velocity divided by space. And that's Hubble constant units of 100 kilometers per second per megaparsec. That's because until, 20, 30 years ago, we didn't really know what it was. But now we know it's pretty close to 70, give or take a couple. So there's little h sub 70. If you just divide Hubble constant by 70 kilometers per second per megaparsec, that's what it is. And that just kind of simplifies this writing down other equations because you don't have to worry about what happens if somebody recalibrates Hubble constant to 5-10%. The value of the critical density today is about 10 to the minus 29 grams per cubic centimeter. If you were to smear the universe, dark matter and all, and dark energy, this is how much it would be. Matter corresponds to about 30% of that, dark energy about 70% of that. And so you can write down, I'll probably derive for you later on why that is, the equations, if you write down sum of matter, curvature part, which is not real density, it's just fictitious number to make sum equal to 1, and vacuum, they add up to unity, right? Why people like to do this as opposed to just saying, well, it's matter and vacuum and radiation, and that's that. But theorists like this kind of stuff. Okay, so to recap there, the definitions of omega matter is density divided by critical density, which depends on, why do I have an extra row there? I don't know, I have to fix that. Same thing for the vacuum density parameter. Curvature is, again, fictitious density parameter just to kind of add in equations. They add up to unity. If there is no curvature, you have the deceleration parameter given like this. And now if I substitute that in Friedman equation, again, I have to change R's into A's, it's written in the form of these three density parameters which govern the shape of the expansion. Okay? One other thing, which is what I hinted last time, that we kill the holy cow of physics, that energy and momentum are not conserved in the expanding or contracting space, right? And the examples of that, well, look at those photons. They started with some energy, now have less energy, right? A photon that used to be able to ionize hydrogen atom now cannot do it. So photons somehow lose energy. They're not dissipating it. They just have less energy. Two things that had some, they're unbound, but still had potential binding energy due to each other, are now much further apart, they're less bound. And of course, the dark energy comes out of nowhere, so to speak. Universe expands, more volume, more dark energy. And so the reason why this is that conservation laws are really a consequence of symmetries of space-time, which was proven by mathematician Emmy Noether. And if you take advanced classical dynamics, you'll learn all about that. And basically, homogeneity of time gives you conservation of energy. But in an expanding space, not all times are equal. The universe was denser, looking different in the past. And homogeneity of space gives you conservation of linear momentum. Isotropy of space is related to conservation of angular momentum, a specific direction. So this is not something that's unexpected. In some sense, we knew this for a long time, although some people still don't get it. But locally, right, cosmological effects are negligible. And traditional conservation laws on scales are much less than galaxies are very good approximation to reality.